All right, now that we know how to calculate pH, we can now move to finding the pH of a specific acid or base solution. The first question that you have to ask yourself is whether the solution that you're dealing with consists of a strong or a weak acid or base, because that's going to tell you what kind of calculations you're going to have to do. If it's a weak acid or base, there's an equilibrium that's set up, and so the calculations are going to look a lot like the KSP problems did in the previous module. If it's a strong acid or base, it's much easier because it's going to completely dissociate, and you can just take the concentration and go from there. So again, let's do a couple of examples so that we can see what that looks like. Example 7.4 asks us what the pH is of a 0.10 molar hydrochloric acid solution. Now, hydrochloric acid solution, again, first question you have to ask yourself, is that a strong acid or a weak acid? Well, if you have your acids, your strong acids memorized, you should immediately recognize that as a strong acid. When it's a strong acid, the reaction is going to be complete, and there's not going to be any kind of equilibrium set up. So that means that you're going to have HCl plus H2O, and it's going to completely react. So I have a one directional arrow that's going to give me Cl minus plus H3O plus. So at the beginning, before anything starts to dissociate, I know that I have 0.10 molar concentration here, and I don't have anything over here, okay? So this is before reaction. After the reaction takes place, I'm not going to have anything left over here, and I'm going to have 0.10 molar here and 0.10 molar over here, okay? So as you can see, because all of it's going to dissociate, now disclaimer, yes, we have talked about the fact that actually every reaction is an equilibrium reaction, but here the products are so heavily favored that we can assume that it's going to go to completion, okay? So because there's none of this left, I know what the hydrogen ion concentration is. It's 0.10 molar. So from that perspective, all I have to do then is take the negative log of 0.10, because that's what the definition of pH is, in order to find the pH of this solution. And when you do that, you should find that the pH of this solution is equal to 1.00, okay? Two significant figures here, so that means that I have two numbers after the decimal point in my pH, okay? So, relatively simple, right? How about if I'm dealing with a base? What's the pH of a 0.5 molar solution of NaOH? Well, again, first question, strong base or weak base? Well, sodium's in the 1A column, so it is a strong base. And so just like I had before, I'm going to have the NaOH, and then when it dissociates, it's going to dissociate into sodium ions and hydroxide ions. So before reaction, I have 0.500 molar over here, and then I have nothing on this side. After reaction, I have nothing left here, and I have half 0.500 molar of sodium ions and 0.500 molar of hydroxide ions. So again, because it's all reacted, that actually makes this easy. This time though, I'm dealing with hydroxide ions, and so since I have hydroxide ions, what is going to be easy to find is the POH, because that's going to be the negative log of 0.5. Okay, so when I find the POH, I'm going to have 0.301 for that. Okay, three significant figures here, so I'm going to have three numbers after my decimal point for when I find my POH. Okay, then I'm going to take the fact that pH and POH added together make 14, so I'm going to take the pH equals 14 minus 0.301, and that is going to give me 13.3 0.699. So that's going to be my pH of that solution. Now, I believe that what he did in this one is he actually used the KW. He took the hydroxide ion concentration and then found hydronium ion concentration. Again, there's nothing wrong with doing it that way. I just think it's easier to do it this way. As far as significant figures go, do remember that this 14 is exact. It's going to have an infinite number of significant figures. So the fact that I had 3 here means I'm going to have 3 figures after the decimal point here because this is a subtraction problem. Okay. Now, example 7.5, I'm not actually going to work that one for you, but if you go through that, you should see that it looks almost exactly like the KSP problems that we worked in the prior module. You are setting up the equilibrium expression. You're using the Ka that they gave you with the equilibrium expression. You're setting up an ICE table like we did before. And he's saying, all right, so can I ignore this minus X? If I can ignore it, if it's going to be small enough that it doesn't matter, it makes your calculations easy. And so that's what example 7.5 is. Now, example 7.6 is a base. Again, the method for working it's going to be very, very similar. So I will go ahead and work that one for you since we're dealing with the base instead. But it's the same idea as the one that he did for acetic acid in 7.5. So with example 7.6, we want to know what the pH of a 0.50 molar solution of ammonia is. So NH3, strong base, weak base, or strong acid, weak acid, which one is it? Well, he gave you the KB, so if you didn't already know that it was a weak base, which you should have, the KB would tip you off that it's definitely a weak base. So the first thing that we need to do is we need to write an equation for what happens when this dissociates in water. So I'm going to have NH3 plus H2O. And again, this is an equation that we've seen before. I think I had it up here the very first day of the chapter. So this is going to make NH4 plus OH minus. Okay. They tell me what the KB is. So initially, I'm going to set up my ICE table. Initially, what's the concentration? Well, initially the concentration of ammonia is 0.50. This is water, it doesn't matter. Okay, so this is going to be 0 and this is going to be 0. As the equilibrium is set up, I'm going to lose X amount of this on this side and I'm going to gain X amount of it on the other side. So at equilibrium, ammonia is going to be 0.50 minus X. The ammonium ion is going to be X and the hydroxide ion is going to be X. All right. Now I need to set up the KB expression. So KB from my balanced equation is NH4 plus times OH minus over NH3. Okay. I am told that the KB for ammonia is 1.8 times 10 to the minus 5. Okay. The ammonium ion concentration I figured out was X. The hydroxide ion concentration was X. And the ammonia concentration was 0.50 minus X. Okay. Can I just drop this out? Well, again, just like we talked about in module 6, I would have to assume, if I'm going to be able to drop it out, that X is going to be less than 0.005. So if I solve it and my X is actually less than this, then I'll know that my assumption was valid and the amount that this lost is going to be something that I can ignore because it's not going to make a difference in the final answer. When I solve this, and I assume that I can ignore this, we've done these calculations before. I'm not going to go through the nitty gritty of how to work the calculation. You're going to multiply both sides by 0.5 and then take the square root of it. Your X comes out to be 0.0030. And that definitely is less than 0.005. So I know that my assumption was okay. So because this is X, I know that it's also the same thing as what the hydroxide ion concentration was. Okay, so if I know the hydroxide ion concentration, what can I find? I can find the POH, because the POH is the negative log of the hydroxide ion concentration, so it's the negative log of that. So the POH ends up being 2.52. I have two significant figures here, so I've got two significant figures after the decimal point. And then what I would do is, again, why he tends to use, and I think he did here too, he tends to use KW to solve that. I think it's easier to take 14 minus this and come up with my pH. So pH equals 14 minus 2.52, and that is going to give me a pH of 11.48. Okay, remember again, that 14 is an exact number, all right? So last step, a little bit different than he did in the book, but again, I think subtracting this way is much easier than using the KW for water, all right? So these problems shouldn't look a lot different than the KSP problems that you're already used to working. So I will let you get some practice with that.